Let's finalize a naive-based classification. Here we have another example of classification task, uh, which is about classifying, as you can see from here, classifying mammals from non-mammals. And we have four independent variables, x1 and x2, x3, and x4. And the first one is does it give birth? Can fly. The second one is can fly, and third one is live in water, or and fourth one is have legs. And based on those questions, actually, the answers are yes or no, and yes or no, or sometimes. So all those four variables are discrete variables, categorical variables, and we have two classes, mammals and non-mammals. And based on this training set, the purpose of this example is to classify this new animal, this new observation uh, into mammals or non-mammals. So this guy, we don't know about the class of this guy, but this guy gives birth and cannot fly and lives in water and has it doesn't have legs. So based on this, uh, to use the naive-Bayes classifier, what we have to do is we have to find all necessary conditional probabilities, and here's the answer. And actually, this one is the product of the conditional probability, and actually this notation is simplified. And because this one gives birth, uh, what we have to is we have to find the probability, conditional probability x1 equals to yes, given y equals to mammal, and that can be estimated in this way. So we first take a look at the rows having mammal's value on the class variable that are this one and this one, this one, this one, this one, and this one. And in fact, there are 20 observations in this training set, and mammals are 1, 2, 3, 4, 5, 6. Is that right? 1, 2, 3, 4, 5, 6, 7. 7 observations are there. So among 7, the the observations having yes on x1 is this one, this one, this one, this one, this one, and this one. 6 variables. So this probability is 6, and that is this one. And the probability, conditional probability x1 becomes yes given y equals to non-mammal is among the remaining, because there are 20 observations among remaining 13 observations. We have to find the value of x on the value of yes on this x1 variable that are, how many are there? There must be one. Non-mammal. Oh yes, this one. So there's only one, uh, the observation having yes value on x1. So that the probability is 1 over 13, and that is corresponding to this one. So in this way, we can estimate the conditional probabilities, the other things, such as probability x2 equals to no, can fly is no, given y equals to m, and probability x2 equals to no, given y equals to non-mammal. So I think you can find those values. So they are this one and this one. Okay. In this way, you can estimate all necessary conditional probabilities for mammal and conditional probabilities for non-mammal, given y equals non-mammal and given y equals to mammal. And then multiply all those conditional probabilities, and the result is this one, 0.06 and 0.0042. As you can see from these two values, and as I told you in the last session, because the answer is the multiplication of the probabilities, the numbers are pretty small, right? And after that, we multiply the probability, the prior probability y becomes to memel, and this one is the probability, prior probability y becomes to non-memel. That is estimated by counting, just simply counting the number of memels among 20 observations and counting number of non-memels among 20 observations. They are, I'm sorry, they are given here and here, right? So the posterior probability by Bayes theorem is this one for the memel case, memel class, and the posterior probability based on Bayes theorem for non-memel class is this one. And which one is greater? This one is greater than this one. So we classify this new object into memel class. Okay, so now you can, I think, solve a classification problem in this way using naive-Bayes classifier. So in summary, actually this classification method is robust to noise points. The reason is that because we are estimating the conditional probability, and especially in the case for the case of the continuous variables, even though some value on observation, some value is far away from the other values, because we use discretize, or we can even divide into two bins. So even though some specific value is far away from the other values, that doesn't affect a lot to the final classification result. So it is robust to noise points, and it can handle missing values by just ignoring the instances, those observations having the the having missing values, the instances having missing values during the probability estimate calculations. So when we estimate the conditional probabilities, if there is a missing values, we just ignore that the specific observations. For example, let us assume that this one is missing, this value is missing, and this value is missing, and we still want to just like before, we still want to estimate probability x1 equals to yes, given y equals to memel. Then among 7 observations, the observations having yes value on this column is 1, 2, 3, 4, right? Then 4 over 7. In this way, we can estimate the conditional probabilities by ignoring these missing values. So even though a data set contains some missing values, we can still apply the naive-Bayes classifier. But please think about the case of the logistic regression, because we have to solve a maximization problem based on the likelihood function, objective function. So if there is a missing value, we should ignore the entire observation when we define the likelihood function. So actually the logistic regression inherently is not able to handle missing values. And the third one is this method is robust to irrelevant attributes, because the posterior probability is computed by multiplication of the conditional probabilities x given y, and we multiply p of y. So among those there is a irrelevant attributes to the class variable, then actually that affects to both class equally, so it doesn't contribute a lot for the classification test. What does this mean is, for example, there is an independent variable x5 which is not really relative to associate to the class variable y. So for example, for instance, there is a class yes, no, yes, no, yes, no, 1, 2, 3, 4, 5, 6, and then uh, I'm sorry, forget about this. It's kind of difficult to make an example to give you. Let me try again. X5, and there is a class variable. Yes, 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 yes. No, 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 no. So two classes here, and this one is a has the value of x5 takes either a or b, and a, b, b, a, b, b, just like this. So among the examples having y value on this class variable, there are two a's and two b's, and it's same for the other remaining the other four instances. Then actually, this one is not really related to this class variable. It means that actually this variable doesn't make any contribution to the classification task. Then actually the probability x5 equals to a given y equals to y is the same x5 equals to a y. Those two probabilities are the same, so we multiply the same value to the class y and class no, so it doesn't contribute to at all to the classification task. So the naive-Bayes classification method is quite robust to irrelevant attributes. Even though in our training set there are irrelevant attributes, naturally we can naturally ignore those things. And the other one is actually this disadvantage of the naive-Bayes classifier. If because we take the conditional independence assumption, if independence assumption does not hold for some attribute, it means that there's some predictor variables x1 and x2, x3, x3s, and if they are highly correlated, and then uh, the performance of the naive-Bayes classifier may not good. It's possible to have a bad classifier. So actually, what we have to do before employing this naive-Bayes classification is that it's uh, it's better to confirm whether or not there exists uh, collinearity among the, the independent variables. So if this independence assumption does not hold, it's possible to have a bad classifier based on the naive-Bayes classification. So in such a case, actually we can employ another Bayesian classification method, which is such as Bayesian networks. Actually, in this method, in this classification method, actually we can make an dependence structure, dependencies in the network as a format of network. So in such a case, even though there is a some dependencies among among the predictor variables, x variables, uh, is actually this one it shows usually shows better performance than naive-Bayes classification. In in the case that there exists some dependencies among x variables. Actually, in addition to this naive-Bayes classification, there are several Bayesian approaches for the classification, and the one example is Bayesian network, and the other one is Bayesian neural networks, and there are a few more, and but this one, uh, as I told you at the beginning of this session, the naive-Bayes classification session, this one is also one of the most often used method, and sometimes it gives a quite good performance. So it's a good option, one of the good options for classification problems. give it a try whenever you have a classification technique. And as you can see from these examples, actually this one is quite useful for discrete categorical independent variables case. Yeah, so if you have some training set consisting of the categorical variables, this one is a good option. And here is an R example, and this one, so there's a code, so you can just paste and copy and paste into your R session, then you can see the result. And in fact, the naive-Bayes classification can be done using this naive-Bayes function, as you can see from here. But that function, to use this function, you have to install this E1071 package first. So let me show you these things in using R. So we have to first install this package. So go to this package tab and then install, click install E1071, install this package. And then actually this ML bench is short for machine learning benchmarking dataset. And this package contains lots of data sets from real world and quite well summarized. So actually this house vote 84 data set is included in this package. So let us attach this package as well. Oh no, there's no package. So just like the E1071 case, ML bench. Install this package and attach those two packages into your R session. And then to use this data set, we have to use this data function. Then if you run this code, then you can use this household 84 data set. There are 435 observations and 17 variables, and the first one, as you can see from this, the first one is the class variable, and there are two classes, Republican and Democrat. So it was about classifying people into two parts, two classes. Is this guy Republican or something like this? And then by using this command, you can see the first few lines of this data set. And as you can see from here, actually this one is indicates missing value. This NA is shown for not available. So these are the missing values. So this data set is to classify two classes, and then there are 16 independent X variables, and all those are categorical variables, and it contains some missing values. And just run this single line. So this again, this function is in this package, and then you specify formula. By formula, you can specify the class variable, and this one means, again, I already explained about this. The remaining columns will be used to predict the variables, and then the input data training set. Training data is household 84. So just run this one, then it's done. So training naive-Bayes classification, naive-Bayes class training on naive-Bayes classifier is what is estimating all possible conditional, all necessary conditional probabilities. Okay, and because this is the case of two classes, to the prior probabilities. Then by learning, just learn the trained model. So run this code, just evaluate this one. Then you can see from this console window, the result of the training. So there are 61%, about 61% of the data is the Democrat, and about 38% is Republican. So by just counting the number of rows, and we can estimate those prior probabilities and all possible conditional probabilities, we can see those. They are given here, okay? So for example, this one is what? It's a conditional probability V1 becomes V1 equals to no given Y is Democrat, and this probability is the probability V1 equals to what? Yes, given Y equals to what? Democrat. This one is that, right? So you can see all necessary the conditional probabilities from the trained naive Bayes classifier. Okay. Yes, that's the. So you can just install this package and then use this function to train naive Bayes classification. But the question is, at this juncture, I want to give a question. Can you implement this naive Bayes classification without using this function? Can you program it using R? And please try, give it a try to practice. So try to build a function that returns these conditional probabilities and then these prior probabilities. I think you can do that if you are quite familiar with this R programming. I think you can do that. And then actually, I think even though there is no code, you can still use the predict function to predict the class. Predict, and then the trained model is model, and the data set, because we didn't divide it into training and test, so let us just use this whole thing. And then by learning this code, okay, yes, you can get the predicted class. Right, so let us save this one as a pred. Okay, and you can make a confusion matrix using table function. The true value is house boot 84 class, and then pred. You can make a confusion matrix using table function. Then we can see that this many observations are misclassified, and this many are correctly classified. So let us compute the accuracy. The accuracy is saved into x, and then sum diag x over sum of x. Then the accuracy is 90% for training set. So this one is the training accuracy. Okay, so that's everything about the naive Bayes classification, and thank you for your attention. In the next class, we will talk about another classification method. Thank you for your attention. I will see you again.